All right, welcome everybody. In this video, I want to summarize a number of statements that we've been discussing so far in their relation to matrices, invertible matrices, systems of linear equations, systems to matrix equations. We've been making a lot of connections between these different ideas, and I just want to crystallize some of those thoughts and eventually put together a really nice result called the inverse matrix theorem. So let's start by considering four different statements. So let's let A be a square n by n matrix. So here are four statements I've labeled A, B, C, and D. So statement A is that A is an invertible matrix. Statement B is that A is row equivalent to the n by n identity matrix. Statement C is that A has n pivots. And statement D is that the equation AX equals 0 vector has only the trivial solution. So we're going to show that all four of these statements are equivalent, meaning if any one of them is true, then all of them are true. If any one of them is false, then all of them have to be false. So let's start with statement D, and what we'll do is we'll first show that if statement D is true, that is going to imply that statement C also has to be true. So let's take a look at why that might be the case. Okay, so if we are trying to solve this matrix equation AX equals 0, then we could set up an augmented matrix for this system that would look like column vector A1, A2, all the way up to column vector AN, since A is n by n. And then we have a last column, say, of zeros corresponding to the fact that this is the homogeneous equation. And then we can do some row operations on this augmented matrix. And no matter what sort of operations we do, since this last column is all zeros, we're going to be interchanging rows that have 0 in the last column, or adding and subtracting 0 from each other. So whatever operations, row operations we do, it's not going to change that this last column is always going to be 0. So that last column is going to consist of all zeros. But we can reduce this matrix. And if we're assuming that this equation AX equals 0 has only the trivial solution, then what that tells us is we have a pivot in the first column. This would tell me that x1 is equal to 0. I must have a pivot in the second column, since we know that the trivial solution is the only solution. So x2 is going to have to equal 0. And we would do this on and on and on, all the way over. And in the very last column of matrix A, we should have a pivot over here corresponding to xn equals 0. So this augmented matrix has no free variables, and that's equivalent to what we see over here, that matrix A, when it's been put into reduced row echelon form, it's going to have a pivot in every single column. So this tells us that statements D, if statement D is true, then therefore statement C has to be true. And now we'll go up our list and next show that if statement C is true, that matrix A has n pivots, then statement B must also be true, namely that A is going to be row equivalent to the n by n identity matrix. And we pretty much see that as a direct result up here. So there's not too much additional details to prove in, but if A has n pivots, then we know it has to be row equivalent to the n by n identity matrix. Since if it has n pivots, and we're eliminating all of the entries below it and above it, the only thing that's going to be left are going to be the ones on the diagonal. And that's the identity matrix. So now we know if statement D is true, both statements C and B also must be true. Because if D is true, C is true. And if C is true, we know that B is true. So let's next take a look at if statement B is true, how can that therefore imply that statement A has to be true? Okay, so finally, if we know that statement B is true, namely that A is row equivalent to the identity matrix, then this tells us that A has to be a product of elementary matrices. Since we could get matrix A by applying a series of elementary row operations to the identity matrix. And if that's the case, then we can find the inverse of A by taking the product of these elementary matrices, taking the inverse of each of these elementary matrices, and then multiplying them in the reverse order. And that would give us the matrix, the inverse of this matrix A would therefore be En inverse multiplied on the left by En minus 1 inverse all the way down to the very furthest matrix on the left would be E1 inverse. And you can check that multiplying by this matrix on the left of A and on the right of A both would give us the identity matrix back. So therefore, A is an invertible matrix. So at this point, what we've shown is that statement D implies statement C implies statement B implies statement A. So therefore, I know if D happens to be true, then all of these other statements, C, B, and A, are true. If D is not true, then C, B, and A are not true. What I'd like to show is that if A is true, then that's going to imply that D is true. Since right now, all I know is D is true, that tells me that A has to be true. But this implication so far is going in one direction, and it's not circling back in the other direction. So we're going to add some additional statements to this list, and we're also going to be able to connect these implications in both directions. So let's take a look at some additional statements next. Okay, so on the previous slide, we showed that D implies C, that C implies B, and B implies A. And we'd like to circle this equivalence back around so that we can therefore say, in addition, if A is true, then all of these other statements would have to be true. So we're going to add a new statement to this list, namely that if we have an n by n matrix C, so that when we multiply matrix A on the left by C, we get an identity matrix. So we're going to next show that if statement A is true, that's going to imply that statement J has to be true. And hopefully this is a pretty quick implication, since if A is invertible, that means A inverse exists. So we're going to set matrix C equal to A inverse. And then by definition, we know A inverse times A would give us the identity matrix. So if statement A is true, certainly statement J needs to be true. And lastly, to connect this chain, if we can show that statement J implies statement D, then we know that all of these statements are either true at the same time or they all have to be false. But these implications go in both directions. And so if we assume that statement J is true, namely that we have this matrix C so that we multiply on the left of A, we get the identity, then we can show that the matrix equation AX equals 0 has only the trivial solution, because we can take this equation, AX equals 0, multiply both sides of that equation on the left by matrix C, and we have assumed that this gives us the identity matrix. Multiplying the 0 vector by matrix C is going to give us back the 0 vector. So now what I can see is that the only solution here is that X has to be 0. So we only have the trivial solution. So this completes our chain. And now we've shown that all of these statements, A, B, C, D, and J, are all equivalent. If any one of them is true, we can therefore imply all of them have to be true. If any one of them is false, then all of them have to be false.